Hi, everyone. Welcome to our webinar. My name is Sharice, and I'll be your MC today. I'm an AI systems and machine learning engineer at Erandir Mobile, which is a biometric identity company focused on providing identity while granting you your privacy using your unique neurosignal. Like all of you joining us today, I'm really excited to learn more about smarter ways to improve my workflow efficiency within the AI ML space. A little bit about our host today. The organizers of this event are from Data Phoenix. Data Phoenix is a media and education initiative led by Dmitros Vodorets, focused on AI and data. Through over 100 webinars featuring speakers from DeepMind, UC Berkeley, NVIDIA, Databricks, and other leading companies, Data Phoenix has reached over 20,000 engineers like you and I worldwide. Its video production unit covers top conferences such as TechCrunch Disrupt, CES, the PyTorch Conference, the AI Infra Summit, and also supports local AI events in San Francisco to ensure that their knowledge reaches the global community. And it's my honor to introduce our speaker today, Vlad Pavlov. Vlad is a senior director, AI and software engineering at PMG. Before that, he co-founded 3 startups, served as a VP engineering and a CTO in 2 mid-sized companies, and also has a background working at Microsoft and Intel. Vlad is also an open source enthusiast and a machine learning practitioner who won a few medals on CAGD competitions. So thank you again, everybody, for joining us today, and I'm going to just pass it on to Vlad.
Sharice, thank you so much for the introduction, and great thank you for everyone who joined us today, and thank you to Dmitry and Data Phoenix for hosting this event. And the problem that we are going to be talking today about is a problem of resources. When you listen to the news, you see what people are talking about in the media. When it comes to us moving towards AGI, it appears that the main constraining factor seems to be lack of computers and lack of electricity that everyone anticipates is going to slow us down in the future. Eric Schmidt testified in front of Congress saying that, hey, electricity is going to be a constraining factor. OpenAI keeps talking about lack of computing power to be the main constraining factor for them. The same signals are coming from NVIDIA, etc., etc. So basically, that is the something that is going to make it more expensive for people to use AI, more expensive for people to use other resource-intensive applications. And I hope you can see my shared screen. Am I correct? Awesome. So one of the ways to address this scarcity is just to build more factories that will manufacture larger number of processors and build more data centers using those processors and more machines in those data centers, and of course build more power plants. And this is what people are doing. But on top of that, I think we should also be thinking about improving efficiency of the existing programs and improving efficiency of how we are using existing resources and existing hardware. And this is basically the main topic of today's presentation. As Sharice mentioned, my name is Vlad Pavlov. I am Senior Director AI and Software Engineering at a company called PMG. You probably never heard about us. We are a marketing agency. We help large brands, companies like Nike, McDonald's, Apple. We help them running their marketing campaigns. And we are pretty well known in the marketing industry. We are one of, according to Forrester, we are one of top 3 independent marketing agencies in the United States, one of top 5 worldwide. Under the hood, however, we are not a marketing agency. We are a software company that pretends to be a marketing agency. And about 8 years ago, we started developing a proprietary suite of tools, a platform that automates most of the marketing workflows. Just to give you a sense of the scale, last year, our technology powered ad delivery to over 1 billion consumers worldwide. Basically, 20% of adults on the planet were touched by our technology. So this is what I'm doing during my day job, but what I'm going to be talking about today started as my hobby. It started several years ago during COVID when everyone had a little bit of extra time, and I spent my extra time doing data science competitions. I became very excited about Kaggle competitions. I started participating in them. And the way you participate in data science competitions, the way you win there is by creating many, many experiments and trying to out-experiment your competitors and hopefully figure out something that they didn't figure out. That requires a lot of compute resources. I spend a lot of money on AWS. That also requires a lot of your time because you're waiting for the next version of a model to be trained. Once it's trained, you find out, okay, this is the next change I want to experiment with, to play with. So this was about 5 years ago, and this was when I created a small library, which I initially used for myself, just to become more productive as a participant of data science competitions, and I actually won a few medals because of that. But later, a couple of years ago, I realized that the same principles, the same core ideas that were part of that approach, they are actually applicable at a larger scale to what is happening right now. Because right now, to train a model, it could take not just one guy and several computers, it could take a cluster of 20,000 computers, and it could take a few weeks or maybe even months. So if you're able to save at least 30% of that, that by itself is a huge deal. And basically, that's what we are going to be talking about. And the agenda for today is going to consist of 5 topics. The first 2 parts are going to be the longest. We are going to talk about the main ideas that can help us use existing hardware more efficiently while using Python for machine learning and data science. And my goal is to inspire you with these ideas and encourage you to try to apply them. And you can apply them in many different ways. One of those ways will be demonstrated, well, during the demos, which is the second part. And after that, we'll talk more about functional programming, where it is now, where it is headed, because it evolves, of course. We'll have one more demo specifically about some functional programming concepts. And after that, we are going to discuss the next steps, how each of us can benefit from using the ideas which we will discuss at the beginning of the presentation. And before we go there, this is actually why we are doing it at the Zoom. In the morning, the first version of this webinar, when we had way more people, at that point of time, we did it using YouTube. And it wasn't really interactive. And now when we have smaller number of people, we decided to try to do Zoom to make it more interactive, to make it more easy for me to ask questions and for you guys to answer. So my first question now is, if we compare neural networks, artificial neural networks, with human brain, which is natural neural networks, how comparable are they? Specifically, if you are thinking just about one neuron in a human brain, how fast is it? Or to be more precise, how frequently does it fire? How many times a second does an average human neuron fire? And that's the question to you guys. You can answer in the chat or you can use your voice.
It's about 100 hertz.
About 100 times a second, right?
Yeah.
Okay, that's who thinks a human neuron fires more frequently, who thinks it fires less frequently? Any other? Or who agrees? Maybe you guys all agree with this answer, approximately 100 times a second. Come on, guys! Just guess. If you don't have to know it, just guess.
Maybe 10.
10 times a second. Okay, you're more conservative than the audience at the previous event, because at the previous event, someone said like a few thousand times. Someone said, I think when they were rehearsing it, someone said like 500,000 times a second. You're more conservative. I don't know whether it's good or bad, but you seem to be more cautious. Okay, one more attempt. If someone else wants to provide their version of the answer. People, wake up. Okay, if you don't want to guess, this is the correct answer. A human neuron in our brain, on average, fires every 6 or 7 seconds. It's extremely slow comparing to computers. And let's compare not one neuron, but the entire human brain, specifically human cortex, the most advanced part of the brain. Let's compare our human cortex with the most advanced server currently available on the market. The configuration that you see on the slide costs about $500,000. It comes with 8 the most advanced, top-of-the-line GPUs. So as you can see, it's about 1,000 times more powerful than human cortex in terms of number of operations per second. So it's about 1,000 times larger number of operations per second. It's about 20 times smaller memory, and it consumes way more electricity. Let's forget about the electricity. Let's just look at the ratio between memory and performance. It appears that modern computers, top-of-the-line computers, are very fast, but they're using little memory. And the human cortex is kind of slow, but it uses a lot of memory. Maybe we can spy on the nature. Maybe we can learn something from the nature from this. And this is where we come to functional programming, because functional programming advocates for using pure functions. Pure functions are functions that are, number one, for the same inputs, always produce the same output, and number two, have no side effect. No side effects. And that makes it possible to use a technique called memoization. When the first time we call a function with some specific combination of inputs, the function gets executed, but the next time we call this function, instead of re-executing it again, we are reusing the previous results. And in order to do that, we store those previous results in memory, in RAM. This is a well-known technique which has been used for many decades. The only problem here is in the word RAM. Once we restart our program, or once we restart our computer, RAM is emptied. The entire process has to start again because the cache disappears. But what if, instead of storing these intermediate results, the cached results, in RAM, we would store them, number one, in a persistent cache that will survive restarts of the computer, and that will store the results basically forever. And number two, we make this cache distributed and globally available, so it doesn't really matter who stores the results in that persistent cache. They instantly become available for all the other computers in the world. So let's say today, Sharice, as a part of her workflow in her program, she uses some code that uses some inputs, and it gets computed and stored in the cache. Half a year later, when in my program, which could be a totally different program, but it has this same piece of code inside that has to compute something based on exactly the same inputs, because Sharice already did it, it doesn't have to be recomputed for me, and half a year later, it is instantly available for my program from that global cache. And theoretically, we can think of basically turning the entire planet into this huge computer with huge cache, where all the results, whatever is computed, is always computed just once, and never that computation is repeated in the history of our civilization. All the computation results are stored there forever. And we did some basic modeling, and apparently that's going to increase if this global cache exists. It's going to increase the overall efficiency of long-running workflows, and we are talking about workflows like weather modeling or drug discovery or AI training, something which is very slow and very expensive, it can accelerate the overall process at least 3x times. Sounds wonderful, but of course, probably not possible. What is the probability that enterprise, and of course, most of the compute happens in the enterprise, what is the probability that enterprise would agree to make their data stored in some central place on the planet? Of course not. It's their most important, most valuable asset, right? Their data. Data is, as we know, is new oil. And I agree with you. Yes, of course, enterprise is not going to allow to store their data in one place on the planet, except for 15 years ago, if someone asked you, is it possible that enterprise would agree to store their source code, the most important intellectual property, the most important asset, somewhere in one place on the planet, you would say, no, there is no way enterprise would do it, right? But right now, 99% of the source code is stored on GitHub. So I can imagine that maybe 10 years from now, there will be this GitHub 2.0, when next to all the source code on the planet, there will be all the execution results for all the possible computations of that source code with different combinations of inputs. It may or may not happen in the future, but let's be realistic. This year, it's not happening. However, what could happen is creating this cache on the enterprise level, one cache inside the company that stores all the intermediate results of all the computations inside the company. That can easily happen. That we can easily see. That by itself is going to accelerate those expensive, slow-running, resource-hungry processes at least 2x. So this is actually quite a big deal. And of course, it's worth using. So that was the first idea, basically replacing compute with storage. Remember, brain has a lot of memory, but it's not super fast. Modern computers are super fast, but they have little memory. So let's try to replicate what the nature is doing. Let's replace compute with storage. The second idea is, let's look at what humans are doing when they're sleeping. Technically, the brain is idle. The brain as a computer is doing nothing, right? It looks this way. People are just sleeping and they're not responding to whatever is happening outside. Reality is the brain is working hard, consolidating the memories, processing the data, doing the learning, even doing the simulations. So when it appears that the brain as a computer is idle, in fact, it's doing something. Can we use idle computers? Can we do the same with actual computers? And basically, this is the second idea. And let me ask you the second question. Thinking of the enterprise, on average, what is a utilization rate for servers in an average enterprise? And this is well-researched subject. Maybe you already know the answer because you read some reports. Or maybe you can just use your common sense to guess. Whatever it is, just give me some number, some estimate. What is a typical utilization rate for servers in an enterprise? Come on. Okay, someone said 40%.
40 is a good
Raj
guess.
said 40%. So Raj believes that 60% of the time servers are not busy. Any other idea who thinks it's more, who thinks it's less? Should I pick someone?
It's okay to be wrong, guys. Totally fine. It's really just answering for fun.
10 to 30%.
10 to
How
20?
much? 30? Oh, 10 to 20?
Around 30%.
Oh, 30. Oh, interesting.
Yeah.
Under 30%. Okay.
We have a really conservative group this time.
Okay. So the right answer is it is well below 30%. So if we are talking about, say, mid-size, small enterprise or small companies, it's closer to 20%. If you're talking about huge companies like hyperscalers, it's closer to 50%, maybe to 45%. But on average, it's well below 30%, which means that most of the time, the servers are doing nothing. So if you had a way to efficiently deploy those long-running expensive workflows, which we're talking about, deploy on those underutilized servers during the time when they are not used, we would basically triple the server fleet for an enterprise without investing extra resources into hardware. And people tend to buy extra servers for obvious reason. They try to provision for or over provision for peak load, but reality is, of course, peak load is rarely happening. And there is a reason why at this point of time, those underutilized servers are not used, because it's hard to parallelize at scale, especially when they're not really we don't really know how many servers are going to be there in advance, and they have different configurations, etc., etc. But let's just think about it. Theoretically, we can just triple the server capacity of most of the companies, or at least triple. Let me ask you even bigger question. It's not only about enterprise, it's not only about servers. What is the number of all the devices in the world that are GPU equipped and that are not doing anything at any single point of time, including the enterprise desktops and laptops, including consumer desktops and laptops, maybe not including smartphones, even though smartphones also come with GPUs right now, but let's not count them. Let's just count proper computers that have keyboard, that have the screen, and of course that have GPU. So bazillions. Interesting question, interesting version, Sharice. But yeah, try,
I mean,
guys,
I know
try to
the
guess.
answer. I
Try.
just want to prompt
Yes,
more.
Sharice
more
knows the
questions.
answer, of course.
Yeah.
What? Just guess. Someone who hasn't guessed yet. What do you think is approximate number? I mean, if you just joined, why don't you try to give an answer? No estimates? No guesses?
Yeah, so I would say like around is it you want it in terms of percentage? If I were to say that since it's mostly for an inference point of view, I would suggest like more than half, I guess, because inferences would not be happening at like continuous space. So whenever an inference comes, there would be a peak. So the rest of the time, ideally, it would be not utilized as much, I guess.
So basically, you're saying 50% of all the devices in the world, and then we need to estimate the number of devices in the world, and that would give us number of idle devices in the world. Well, let's keep the math. The number of underutilized computers in the world at any single point of time is about 2 billion devices. Think about it. 2 billion GPUs at any single point of time are sitting there doing nothing. And of course, those GPUs, they're not the same type of GPUs that come with servers. These GPUs which come with servers, top-of-the-line GPUs, they're way more efficient. But the number 2 billion is huge, right? So if we had a way to efficiently use that resource, at least some part of that, that would be a huge help in terms of running those expensive workflows. And if you're thinking about those expensive workflows, let's be clear about what we mean by expensive. The slow running, resource-hungry workflows only in the United States, the amount of money spent on those is about over $100 billion a year. So if we could cut it, say, in half, that would be a huge amount of money that could be spent on something better. But again, I'm far from the idea, and yes, it's not exactly 2 billion, it's a little bit less. 2 billion is kind of approximation. This is the more precise estimate for Q1. This year, I suspect that now this number is larger. Maybe it's even above 2 billion already. But I'm far from the naive idea that somehow we will be able to harvest all that power tomorrow. Maybe we'll never be able to use all those underutilized devices, but we can use the devices which are part of the enterprise. Those where 70% of the servers are sitting idle at any point of time, which is about 50 million servers worldwide. As I said, if you can figure out how to use them efficiently, it will mean tripling the server fleet for a company. And that again brings us back to the idea of using functional programming, again to the idea of using pure functions. Because one of the properties of pure functions is referential transparency. This is something that allows for memoization. But there is also another property of pure functions, which is again a sequence of referential transparency. They allow for deterministic parallelization. In a normal settings, traditional approach to parallelization is not really deterministic. We don't know in which sequence different computers or different nodes or different threads are going to execute different parts of the source code. And that results in all those bad things like race conditions. But if you are trying to parallelize code which is based on pure functions, there are no race conditions there. They're just impossible. It doesn't matter in which sequence they're executed, the results is going to be always the same, which makes it way more easy, number one, to optimize their execution across many computers, and number two, to scale it across huge number of computers, tens of thousands, hundreds of thousands, even millions. So let's go and see how we can use all these ideas in practice. And for that, I'm going to use Pythagoras. I mentioned at the beginning that during the COVID time, I started working on this small library. Over time, it became not small. Right now, it's almost 20,000 lines of code under the hood, and it keeps evolving. And that allows to use all the benefits which I just described. So let's go to the example. And I'm going to use Google Colab, which is basically Jupyter Notebook in the cloud. You don't really need to read all the explanations here. These notebooks are going to be, they're already publicly available, and the link to the presentation will be published after the webinar, and the links to the Colabs are inside the slides, so you can find them later and look at them if you want to. So don't look at the explanations right now, look at the code which I'm executing. So what I'm doing, I am installing Pythagoras and doing the imports. And then the first thing I do is I create a portal. A portal is basically a storage. It's a place where we will store our persistent cache. From conceptual point of view, a portal could be something as simple as a folder, and this is exactly what we are doing right now. We are just creating a folder on a local disk. But it could also be a shared folder, say using Dropbox or NFS. Dropbox, I don't even know how many concurrent connections it allows, probably a few hundred, but NFS allows up to 25,000 connections. So we can have 25,000 computers in this virtual cluster of computers working with the same shared cache. And if you want more, we can use S3 as a storage. In this case, we can have millions of computers connected to the same portal. And from the perspective of a program, a portal is a kind of a window for the program to the outside world and to what is happening with other instances of the same program running, or maybe other programs, different programs connected to the same portal. It kind of connects them through space and time. So we created this portal, which is, as I said, it's basically a storage, a shared storage. And then let's create this long-running function. Obviously, right now it's a fake function. It doesn't really do a lot of meaningful work, but it runs for 5 seconds to illustrate some kind of expensive function that can run for a long time and maybe use GPU or some other expensive resources. And then, number one, I'm using this decorator pure, which comes from Pythagoras. And of course, you can only apply it to really pure, to those functions which are actually pure. Same inputs result with the same outputs and no side effects. And on top of that, there is one more requirement. The function has to be autonomous, meaning everything that function needs has to be inside the function. Why? We'll talk later about it. We don't really know in advance on which computer this function is going to be executed. So maybe on this computer, maybe on some other computer. So we don't really know what is happening outside of the function. Everything the function needs has to happen inside the function. So let's execute this cell. And now let's see how this function works. We call this function with some inputs, and of course it executes for 5 seconds and produces some simple result, some number. The next time we call the same function with the same inputs, the result is available instantly, which by itself is not a big deal. There are other memoization libraries that allow you to cache the results. And obviously, one of them is actually standard library that comes with Python, functools, I believe. It allows to store the cache in memory. But here, the cache is persistent. When you restart your computer, the results are still going to be there. When you use a different computer, if it has access to the same portal, the results are going to be there technically forever. Let's call this function with some other inputs. Of course, because the inputs are different, it's going to compute for some time. But then when we use the same inputs for the second time, the result is available instantly. But what if we change the source code for the function? It happens all the time, right? People refactor the code, they change the behavior. Let's do exactly that. And let's see what happens if we call the same function, the same meaning it has the same name, but the body has changed, the algorithm inside has changed. And Pythagoras is smart enough, it realized that the source code has changed, and because of that, the function is executed from scratch, and the result, as we can see, it's a different result now, is stored in a persistent cache. The next time we call this function, again, the result is going to be instantly available. But what if we realize that we made a mistake? The change we made to the source code was wrong. We need to roll back. Let's do exactly the same. Let's use the previous version of the source code and call this updated or revert the back version of the function with the same inputs which we used before. And of course, the results are instantly available. So Pythagoras tracks changes in the source code of the functions, and for different versions of the source code, it tracks all the inputs that were used, and all of that is cached. But what if we use the same logic of a function, but we just make some cosmetic changes? Specifically here, I added a docstring, I added a few comments, and I changed formatting. Let's see what happens. Well, I'm calling the function with the same inputs which we used before, and the results are instantly available. Pythagoras is smart enough to realize that we only made cosmetic changes that didn't really impact the behavior of the function. Because of that, the cached results were reused. And for a portal, there is this method, there is this method called describe, which shows what is inside the portal. For now, let's take a look at line number 1 that shows where the portal is located. It's literally just a folder. As I mentioned, it could be S3 bucket on WS. It can be a mounted folder, which is NFS folder, or if we deploy it over AWS, it could be AWS EFS, Elastic File System, or it could be something else. But it's just a storage. It's just a place where the data is stored. So we don't really need like proper backend, which is always running. That's the first point. The second point, it cached 2 execution results for 3 different combinations of source code plus the inputs for some functions that we used. But it also cached some other values. And basically, this is the idea that we are using here. We are replacing compute with storage. Everything that is potentially cacheable is cached. All the intermediate values, including the source codes of all the functions that we created. And this is the beauty of this approach, because the compute is expensive and slow, and storage is fast and cheap. So we're replacing compute with storage. And the more computers, the more programs connect to the same portal, the larger number of values is going to be stored in that portal, the beta is going to be the hit rate for the cache. The beta is going to be acceleration and optimization that each of the programs is going to benefit from. It's very similar to social networks. The more people connect to the same social network, the bigger is the value that each individual participant gets. So basically, that's the first example, the example that demonstrates how we are using persistent memoization. Let's go to the second example, to the example where we are talking about deterministic parallelization. The same story, I'm doing the imports, I'm creating a portal, but now let's talk more about portal. I told you a few minutes ago that a portal is just a storage. Well, it's not just a storage. It's just half of the story. The other half of the story, let's call the describe method. And now let's look at line number 10. There are also so-called background workers. So every time a program connects to a portal, in addition to the main process where the program runs, it's also going to launch a few background workers. The number of background workers it's going to launch is going to be different depending on how much unused resources are currently available on that specific computer. Right now, for example, it launched 2 background workers. It could easily be 5 or maybe 0, depending on the utilization rate for this specific computer. Those background workers, they're totally independent from the main process, from your program. They basically kind of do nothing. They just look at the portal. They're waiting for someone to place an execution request into a portal. When you have your pure function, you can execute it inside your program, but instead you can place an execution request to the portal and say, hey, maybe someone will execute it for me. And then the first of those workers that sees a piece of work to do an execution request, it grabs this execution request, it tells everyone else, hey, I'm working on it, and it starts executing it in the background. And you don't know in advance if there are many computers connected to the same portal, it means that there are many background workers working on all of those computers. There is a swarm of background workers, and you don't know in advance which of those workers is going to grab your piece of work and which of the computers is going to be used to execute it. And this is totally decentralized, totally heterogeneous system where there is no one central coordinator. There is no one backend that coordinates and decides which work is going to do what. There is no scheduler. Everything is happening totally decentralized, totally asynchronous. The actual backend is just storage. Cheap, persistent, very straightforward storage. Let's see how it works. We are creating the same function. We are executing this function with some arguments, basically the same inputs that we used before. But now the next time we are going to execute it, we are going to execute it using the swarm method. A swarm method is very simple, similar to other to what is done by other libraries that offer asynchronous execution. It's going to place an execution request somewhere, and it's going to return an address of the future result. And then we can check whether the result is actually available or not by using another function called ready. So let's call this swarm method with some combination of inputs, and let's check this ready method. And of course, ready returns false because it's not ready. But while we are talking, I sincerely hope that Pythagoras is not going to betray me. And one of the background workers actually saw that execution request and started working on it and actually executed that function in the background. Let's call this function ready again. Yes, now it returns true. So someone in the background already executed it, and we can use the get function to get that result executed in the background. And of course, in this very naive demo example, we are using just one computer, which is the cloud computer provided by Google for this Colab. So obviously, this time it was executed by a background worker on this computer. But if there was a second computer that was connected to the same portal, we wouldn't know which one executed it. There is no way. And as I said, it's totally decentralized thing. And if you look at the describe method, it's going to show us that there are 2 cached execution results. One was called synchronously, The other one was called asynchronously. And yes, it shows that there are two background workers. And yes, it shows that the execution queue is empty. But we are talking about a large number of computers. We don't know in advance what are those computers. Maybe some of those computers are not equipped, not capable to execute the code that we wrote. To address this, there are pre-validators and post-validators. Pre-validator checks preconditions, post-validator, well, checks post-conditions. And in this specific case, pre-validator checks whether there is a specific package installed on the computer where a background worker tries to execute a function. If this package is installed, fine, on this computer, the background worker will try to execute this code and return the result. If the package is not installed, first, the background worker is going to try to install the package. If the installation is successful, then the background worker is going to proceed and execute the code. If not, a background worker is going to give up, and some other background workers on some other computers will try to execute it. But of course, we are talking about Pandas. Pandas is installed everywhere. So when we try to call it synchronously, the result is going to be available immediately after the function ends execution because Pandas is here. And when we swarm it, again, it's going to be very fast, but let's take a look. So we called swarm with some other inputs, and we look at the describe. Look, describe shows us that there are 3 cached execution results. 1 execution request is in the queue, and as before, there are 2 background workers. While we were talking, I hope that one of the background workers took care of that execution. Yes, it did. Now we have 4 execution results cached, and the execution queue became completely empty. So basically, that's the beauty of this approach. And there are many different pre-validators. For example, we can check what is the amount of unused memory available on this computer, not the overall number of installed gigabytes, but the number of gigabytes which are currently available for this function to be used. Or we can combine different pre-validators. Here we check whether there are 2 packages installed and whether there are at least 10 CPU cores available unused on this computer. And you can write your own pre-validators because they're basically just functions that are checking the current environment. The same way, there are also post-validators that can do some basic check and see whether the results returned by the function make sense, kind of unit tests, if you will. And basically, that's it. I hope you got the idea. And the main beauty is the same as before. The larger is the number of computers connected to the same portal, the bigger is the swarm of background workers, the larger is the overall power of this virtual cluster of totally asynchronous, totally distributed, totally decentralized computers working together. So the main beauty here, there is no central scheduler, there is no central orchestration engine. Whatever is the backend for everyone is just a storage. Amit is not mute anymore. I assume it means Amit wants to either ask a question or give a comment.
I had a just quick question. So you mentioned that for the post validators, assuming we are actually verifying the overall final output and whether it makes sense or not, right? So at a time for a particular long running job, I'm assuming that only say one worker is picking that particular set of inputs and then trying to process it. And after the processing, it found that the post validator check failed. So we don't have a very useful output from that particular execution result. So what would happen to that particular, assuming that it is a problem with the machine in some sense? So will it be picked up by another worker, or will that particular execution be
discarded? So what is going to happen? There will be exception thrown. The exception is going to be recorded, and I'm not going to the details, but as I said, under the hood, there is a lot of here, including a way to log and monitor and analyze all those exceptions that were thrown on different computers. They all also stored in a portal, so we can later track what happened. Anyway, the exception is going to be thrown. Another worker from another computer is going to pick it up. there will be exponential, and it's not only about results not being generated, even in terms of time. If a worker said, hey, I'm working on this code, but maybe after some time, it didn't produce any code at all, and you can configure the time. It didn't produce any result at all, I'm sorry. Then maybe computer died, right? Maybe power went off, or maybe something happened with the code. So another worker is going to wait some time, and then it will try to execute it again. The time they're waiting is going to be increasing exponentially, and after several attempts, it's going to stop. So current default configuration, the first attempt is going to last for 10 minutes, then it's going to double every time, and there will be 5 attempts by 5 different workers running on 5 different computers. If after the 5th attempt, there is still no result, then it's basically going to go to that letter Q, and this code will be labeled forever as, well, bad code.
Yeah, okay. So we would ideally have the details of all the different attempts made, right? Meaning the first one failed. Assuming that I gave it to say the first computer and that executed, and for some reason the post validation check failed, that would be ideally available in the logs, and another worker picked it up. So, and you're saying that ideally, say in this case, 5 computers reattempted the same piece of code, and all the 5 failed. So ideally, would we have details of all the 5 different attempts?
Yes, exactly. Exactly. And this is the beauty of using pure functions. Ideally, we want them to attempt sequentially, but yes, the world is kind of unpredictable. Cup theorem, we know cup theorem exists, no one ever figured out what to do with it. So there is a chance that there will be concurrent attempts to execute it. And that's fine, because the parallelization is deterministic. Even if there are several computers are concurrently attempting to execute the same code, the result is still supposed to be the same for pure functions. So from that perspective, this is super reliable system. It's as reliable as it's humanly possible. Okay, let's go. Oh my, we only have 5 minutes left. What do we do? Do we cut the other pieces, or do we continue? What do you guys think? Because I definitely have more material to talk than 5 minutes would allow us. Should we spend more than 5 minutes? Or should we finish? Sharice, I believe you are talking, but you're on mute.
I personally think we could probably just continue, and then if somebody has to leave, there will be the recorded piece afterwards that they can rewatch just that end if they miss it. That way you're able to still share all of that content with them.
Okay, I'll try to go through the next slides faster. And if you need to drop, please drop. The recording is going to be available later. So we went through our demos. Now let's talk about functional programming in more details. And again, I feel that you guys don't love answering my questions, but I still have a question for you. What is functional programming? Anyone wants to share what we are actually talking about? Everyone came here because we had functional programming in the title of the webinar, but what exactly do we mean by functional programming? Come on, guys. Well, obviously, it's not just a number, right? It's like the entire definition. It's probably hard to type it in a chat. And there are different definitions. The most interesting definition I saw comes from Uncle Bob, who said, well, function programming is programming without using assignment statement, which kind of makes sense if you think about it. Maybe not always, but at least it kind of inspires you to think in the right direction. But it's more poetic definition, given the specific scope of his book. The way we understood what is functional programming evolved over time. And I actually wrote a blog post about it. In fact, it was OpenAI's O1 Pro who wrote the blog post, and I kind of provided some editorial support for it. And I published it on LinkedIn. You're welcome to read. Actually, it's very, very good overview. If I wrote it myself without using OpenAI, I don't think it would be as good as it is now. So it did evolve over time. From the practical standpoint, the way I'm thinking about functional programming today is number one. This is an approach to programming that assumes that functions are the first-class citizens. What does it mean? Number one, it means that you can store function in a variable or in a data structure. It means that you can pass a function as an input to another function. It means that a function can return a function as an output, or maybe you can even dynamically compose function during the runtime. So that is the biggest part of it. We're working with functions as the first class citizens. Engineers are encouraged to use pure functions. We already talked about those, which means basically there is no mutable state or there is no mutability. So the data is immutable. If you create a new value, instead of assigning it to existing variable, you just create new variable, new copy of this data. Engineers are encouraged to use declarative programming style. Tell computer what you want to do, not how you want it to do. And of course, everyone's favorite, recursion is encouraged over loops. And someone mentioned in the first version of this webinar that you need to know what recursion is in order to define what recursion is, which is probably true. And Pythagoras actually supports all these features of classical functional programming. I am not going to run it right now. This time I'm going to show you the outputs which are already pre-recorded. Why? Because some pieces of code are actually going to take some time to execute. But basically we are doing the same stuff. We are importing, installing Pythagoras. We are doing the imports. We are creating a portal. And then we are creating a pure function. In this case, it's classical factorial. Recursive function which basically computes multiple of all numbers from 1 to n. And it can compute the factorial for 50. It's some large number. It takes some time to compute it for the first time, but the second time we call the same function with the same inputs. Well, this is going to be way faster now. But reality is, in case for factorial, this acceleration is not really dramatic. But for example, for Fibonacci and other Fibonacci numbers, another classical example, Fibonacci numbers is actually a very slow function if we implement it as a recursive function, because the same computations are repeated basically exponential number of times. Here, the acceleration is huge. Without using memoization, it would basically calculate forever. And for Fibonacci number 100, it's pretty fast. I mean, it's 3 seconds to calculate the first time. The second time, if you called it for the second time, the result would be available instantly. But even the factorial, let's say, if you wanted to use the factorial function with no decorator, just normal Python function, and use it, this recursive version of the function, in normal environment with some large input, say in this case n is 1000, the function wouldn't compute. Why? Because the limit for the call stack in Python, and by default it's, I don't even know what is the default value, but it's below 1000. So when we try to call this recursive function with 1000 as an argument, as an input, it will say, hey, maximum recursion depth exceeded. Yes, we can change this setting, but anyway, there is this setting. And if we apply our decorator pure, still it's not going to change much, because still the function is the same. It's using the same Python. Still the Python has the same limitation. So when we call the decorated function with the same large number, as you can see, it returns even larger number of exceptions. even larger error message. Of course, when we applied pure decorator, we know now the results are memoized, so we can play some dirty hacks. Like first we can compute factorial for 50, then for 400, then for 150, etc., etc. Because all the results are memoized, eventually we will get to 1,000. But that defeats of purpose of using recursion to define complex algorithms in a simple way. But Pythagoras is smart enough, it offers help. It has this pre-validator that allows us to tell Pythagoras that, hey, this specific parameter is recursive. Now Pythagoras is going to do some dirty hacks, some under the hood optimizations that would, under the hood, replace recursion with loops. In fact, it's doing more advanced optimizations. But bottom line, we don't need to worry about those Python limitations anymore. We could even ask it to compute a factorial for 1 million, and it would compute it. And even for 1,000, it computed some crazy large number. I don't even know how many digits are here. And yes, it took some time, but the next time this process is going to be way more faster. And since we are talking about a persistent cache that is going to exist forever, over time, these computations are going to accumulate and make the subsequent computations faster and faster. But if you look at the portal right now, what we see, yes, it stored all the 1,000 intermediate results for all the previous values below 1,000. The factorial is already ready to be used. Is already ready, sounds weird, but you got the point, right? It's already here for you to use instantly. And as you can see, it actually stored huge number of some other intermediate results, which are going to be reused in the future when we try to compute factorial for larger inputs. But factorial is kind of basic example. Let's take a look at some other basic examples. Mapping. We have a function that takes a list as an input, and it also takes as an input some other function, which is supposed to transform every element of the list into something different. And basically inside this mapping function, we apply the transformer to each element of the list. And then we are creating this function, which is transformer. In this case, it just returns squared value. And we are calling our mapping function with some lists, some numbers, and this squaring function. And it returns the result. There are two benefits here. Number one, the next time we call it, it's going to be super fast. And number two, even the first time we are calling it, it's going to benefit from all those optimizations which come with deterministic parallelization. But we can take it one step further. We can use our original function, which is mymap, and fix one of the inputs, bind it to specific value. In our case, we are binding it to the value of that transformer function. As a result, we create a new function. So we take an original function, which takes two inputs, and we are creating a new function, which takes just one input. And the other input is basically fixed with some specific value, in our case, this transformer. So we are getting this new function, we are creating this new function on the fly, which is my square map, and we can use it with different lists, with different numbers, and instantly get those outputs. And again, benefit from all the under the hood optimizations that come with deterministic parallelization. And if you put it all together, if you want to spend some time thinking about how to use all those techniques in some extreme cases, here's an example. Two mutually recursive functions, which is not easy to implement in Pythagoras because remember, they are also supposed to be autonomous. Everything that the function needs has to be inside that function. So how do we do mutually recursive functions? Well, here's an example. I'm not going into the details. If you want to, you can take a look at this example later and figure out how exactly it works. But anyway, that was an illustration how you can use traditional functional programming with Pythagoras. But what is the future? Where the functional programming is going to? As I mentioned, it has evolved. Every 10 years, the understanding of what functional programming is kind of changed. I think the next organic step for functional programming, maybe we should call it functional programming 2.0, is planet scale execution model. Because yes, we all know that functional programming allows us to benefit from memoization, and we discussed that we can make memoization persistent. But I believe the biggest benefit of using functional programming comes from deterministic parallelization that allows us to run huge workloads at scale and parallelize them at scale. And scale actually matters. At this point of time, the best technology available on the planet allows you to manage a cluster which is about 20, maybe 25,000 computers. There is no technology that allows you to parallelize your workflows over larger clusters. Why? Because for non-deterministic parallelization, it's hard to manage this kind of workflows. It's maybe even impossible to manage larger number of computers in a cluster. But if we are talking about functional programming and pure functions, we can easily manage clusters with millions of computers, which is probably not something which is of demand right now, but I can easily see with the speed of development of AI how this is something that is going to be of demand in a few years. But that also brings us, if you're creating this planet scale execution model, when we turn the entire planet into huge computer with huge cache and huge cluster of computers nodes working in parallel, then of course we need to support an option when there are many alternative versions of the same code that can run in parallel without conflicting. So this support for multi-versioning of the core code is also something super important. And in terms of what should happen under the hood, we should think about two things. Number one, how do we actually address the values? I used to study C and C++ in a college, and in C, each value has an address, or each variable has an address. This is where the value is stored. And this is basically an offset in RAM. And the same value can be stored in different places and have different address. When we are talking about planet scale computer, we can't use this approach. Instead, we should use content addressing. When it doesn't really matter where your value is stored, the address is always the same. And the way it works is basically we are computing a hash of the value, and we are forming the address based on this hash. So this is the first core principle. The addressing is based on the value regardless of where exactly it's stored. And the second fundamental principle is protected execution. There are several protection levels required. Number one, if you want to have many computers that can run some code, we don't really know if I'm an owner of this computer. I don't really know who wrote this code, and maybe this code is going to be harmful for my computer. So the execution should be protected, should be secure in an isolated environment, no matter what is inside that code. It has to be isolated from my computer. It has to have no way to, I don't know, access my files, delete my files, and do some other harmful stuff. That's one thing. But also, when we execute it across this huge number of computers, we have no way to trust those computers. We don't know whether they're cheating or whether they're really executing that code. So we need to have a way to check whether the output of function is actually something that we expected. And an example of a practical tool that allows to do that is the post-validators. So these are the fundamental principles, and I believe the biggest next step here is going to be creating this planet scale execution model. And I believe it's inevitable because I don't see not only better way to scale existing workflows, but I simply don't see alternative way to scale existing workflows. And with that in mind, we are almost finishing. What are the next steps? How you guys can benefit from this and how you can contribute to this evolution? As I mentioned, Pythagoras is an open source project. It's available on PyPy. You can experiment with this. I don't think it's production ready, but it's experiment ready. So I encourage you to play with it and see. And maybe for your workflows, it's already good enough. But if it's not, number one, I would like to hear from you what kind of workflows you have, what kind of problems or challenges you want to address using technology like this. And please reach out to me and we can chat, and maybe I can implement some additional functionality that is currently not available in Pythagoras specifically for your use case. That's number one. So basically I'm looking for pilot users. And number two, it's an open source project. So far I've been the only person working on it. And as I said, it's pretty substantial project, about 20,000 lines of code already. I hope that eventually there will be many developers, and maybe my contribution is going to become tiny, and it's going to be self-managed, self-supporting community of people working on this project. So if you want to contribute as a developer to this open source project, again, please reach out to me and we can chat. There is a million of things that have to be done there. There's huge backlog. The best way to communicate with me is through LinkedIn. If we are connected, just send me a message. If we are not connected, send me an invite on LinkedIn, and obviously I'm going to accept your invite. And after that, let's chat about one of those two topics. Basically, that's it on my side. If there are questions, I will be happy to answer them. No questions? Well, if there are no questions, I guess I'm going to say thank you to everyone who joined us today. I know it's morning your time. I know oftentimes engineers are people who are evening people, not morning people. I'm an evening person. It's very hard for me to wake up in the morning. It would be perfect for me if people started their work day at 1 p.m. That would be perfect morning for me. So thank you so much. I appreciate you joining. Thank you so much to Data Phoenix for hosting this event. Thank you, Dima. And of course, thank you, Sharice, for helping with doing this and for emceeing and hosting it. And I hope to chat with all of you in the future. And I hope that Pythagoras is going to be helpful for you. Thank you, guys.
Bye. Thanks for coming, everyone.